This is the video for problem 216 in Engineering 623. In this, the problem from the Posar book says, the transmission line circuit in the accompanying figure, and you see the figure right up here, has VG equals 15 volts RMS, ZG equals 75 ohms, Z0 equals 75 ohms, ZL equals 60 minus J 40 ohms, and L equals 0.7 lambda. Compute the power delivered to the load. So we are first going to do this problem. You can see here that I've used the title for the OneNote page, 216 brute force method. So we're first going to use a brute force method to solve this problem, and then we will do it using an easier but less general technique. Now, this brute force method that I'm going to show is completely general. In other words, to be specific here, the impedance of the line does not need to match the source impedance for this brute force method. For the easier but less general method that we will that we'll talk about next, it is necessary that the characteristic impedance of the transmission line matches the source impedance. But if you were faced with a problem where they don't match, this method is the one you would want to use. So we can say, in order to find the power delivered to the load, we need to find the power going down the line. And to do that, we need to find this input impedance. And to find the input impedance, we need to find the reflection coefficient here at the input to the line. So that's what we do. That's what we begin calculating, is gamma of negative 0.7 lambda. And that's equal to gamma. This gamma here is gamma of 0, e to the j beta times minus 0.7 lambda. And when we plug in here that beta is equal to 2 pi over lambda, this becomes gamma of negative 0.7 lambda equals gamma e to the minus j 2.8 pi. Plugging in now, going ahead and calculating gamma, which, remember, this gamma alone is gamma of 0, and that's ZL minus Z0 over ZL plus C0. And so if we do that calculation, we get this quantity, and we can put that in polar form to get this. So now, if we substitute this quantity for gamma into this equation up here for gamma of negative 0.7 lambda, we'll get gamma of negative 0.7 lambda is equal to this. And now we just have to do some complex arithmetic to find out that gamma of negative 0.7 lambda is equal to this. Certainly, if it's not clear already, in these kinds of problems, it is a tremendous help to have a calculator that can handle complex numbers. So this is the gamma at the input of the line. Now that we have that, we can find the input impedance, and it's equal to Z0 times 1 plus gamma at the input over 1 minus gamma at the input. So Z0, remember, is 75 in this case, and then substituting for gamma of negative 0.7 lambda in the top and bottom, we get this. And so Zn is equal to this quantity here. Now we treat this as a voltage divider, and we have Vn is equal to Vg times Zn over Zn plus Zg. And so Vn is equal to this, and we remember now that this 15 is volts RMS. That was the source voltage Vg, and remember that was 15 volts RMS. So this Vn is in volts RMS. Now that Vn is V at minus 0.7 lambda. And according to our formulas for the voltage along the transmission line, that is equal to V plus times e to the minus j beta times minus 0.7 lambda plus V minus e to the positive j beta times minus 0.7 lambda. And so now we just do a little bit of manipulation on that to get that written in this form. And we know 1 plus gamma of negative 0.7 lambda from above, so we can substitute for that. This term is e to the j 1.4 pi. The v plus comes down, and so now we're able to solve for v plus in terms of this vn, which we have just calculated above. And that's important here because our formula for the power is in terms of v plus, so that's why we're doing these steps here, is we want to find v plus so that we can use that formula. The formula here is equation 2.37, which we will get to shortly. So here we have substituted for v plus, and if we go ahead and do the complex calculation, we get that v plus is equal to 7.5 e to the j 1.885 volts RMS. Now, the equation in the book that deals with the power, average power delivered to the load, is 1/2. It's this equation right here, but with a 1/2 out front. But that 1/2 is the appropriate formula for when the voltages are given as peak voltages. But this is an RMS voltage, so the 1/2 disappears in that case. So in that case, equation 2.37 becomes this, that the average power delivered to the load is this, and we've calculated gamma above, we have calculated V plus right here, we know Z naught, and so if we substitute in everything here, we get P average is 0.681 watts. And once again now, this is the method that you should use if you have a problem like this and the characteristic impedance of the line does not match the source impedance. Now we'll look at it. Well, one final comment is this method is not too hard, but there was a good bit of calculation here that had to be done. A lot of complex math, a lot of punching on the calculator. And so fortunately it turns out that there is an easier method, but that it's less general. It requires that the characteristic impedance be equal to the source impedance. So let's look at that more that easier method now. So we're looking at the same problem. Zn is equal to Z of negative L, which is equal to Z naught times 1 plus gamma of negative L over 1 minus gamma of negative L. This is an equation that we used in the previous analysis. Vn is equal, this is the voltage divider, so this is also an equation that we used in the previous analysis. And this is the equation for Vn, since Vn is equal to V of negative L on the line. And this also is an equation that we used in the previous analysis. So, continuing to work with this equation, we just come down to here, and the manipulations here, just standard manipulations. And here we're solving for V plus, and we get this, which now let's see. Notice that and going from this equation here to this equation, we have substituted for Zn. Remember, we began this problem by solving for Zn. Well, now we finally use what we found there and plug in here. And in going from this equation to this equation, we have just multiplied the top and bottom of the fraction here by 1 minus gamma of negative L. So that goes away here, it goes away here, and then we need to multiply it in by this, and also, well, that's it. So that's all we have to do. And then we've also here gone ahead and multiplied out. After multiplying the top and bottom by 1 minus gamma of negative L, we've gone ahead out and multiplied out the denominator to get this. So now look at this expression right here for V plus. Now we remember that V plus, if you know, it appeared in that formula 2.37, and so if we can find this V plus, then we're ready to go ahead and solve the problem. Well, this right here is not necessarily an easy expression to evaluate, but in one case it's very easy to evaluate, and that's when the characteristic impedance of the transmission line, Z0, is equal to the source impedance, Zg. And that happens to be the case for this problem. So let's go ahead and use that fact. So if Z0 is equal to Zg, then we can go ahead and substitute Zg here and here, and then that then every term in this fraction will have a Zg in it, and we can cancel it everywhere. And then we'll be left with V plus is equal to Vg e to the minus j beta L times 1 plus gamma of negative L. And now in the bottom we'll have 1 minus gamma squared of negative L plus 1 plus 2 gamma of negative L plus gamma squared of negative L. And so that now in the bottom will simplify to 2. The 1 plus 1 is of course 2. And then the minus gamma squared of negative L will cancel out the gamma squared of negative L. So we're left with just 2 gamma of negative L. So we have 1 plus gamma of negative L on the top, 2 plus 2 gamma of negative L on the bottom. So this fraction, in this case, the fraction just ends up being 1/2. So we get this very simple expression that when the characteristic impedance of the line is equal to the source impedance, then V plus is simply equal to Vg over 2 e to the minus j beta L. And so just that easily we get V plus. And so in that case, and again, this is only applicable when the characteristic impedance of the transmission line is equal to the source impedance. But when that's the case, then the magnitude of V plus is Vg over 2. And so using 237, once again using taking out the half because these are volts RMS, then it becomes P times Vg over 2 magnitude squared times 1 over Z0 times 1 minus gamma squared, and it becomes 0.681 watts, just as it was before. So that's a considerably easier way to do this problem with much less punching on the calculator. But again, it's only possible to do it that way when the characteristic impedance of the transmission line matches the source impedance. And then there's just a little note here. I was mainly doing this for myself. I was interested to just go ahead and calculate V plus of Z. That's V plus e to the minus j beta Z. And so in this restricted case we're considering here, V plus of Z equals Vg over 2. And remember we found that V plus was Vg over 2 e to the minus j beta L. So plug that in for V plus, and then do just a little bit of arithmetic here, And so we get V plus of Z is equal to VG over 2 e to the minus J beta L plus Z. And of course, then if we're looking at V plus of negative L, it will be equal to VG over 2 always. So it says this is true regardless of the load and also regardless of the length of the line. So that's just sort of an interesting note that the plus traveling voltage wave at the input will always be VG over 2 when the characteristic impedance matches the source impedance. So that concludes our discussion of two different ways of doing problem 216, and that's so that concludes this video.